Before Earth was even a fully formed world, the race for our solar system was already over. The winner was not a rocky planet at all. It was Jupiter, a ball of gas, and it finished forming while Earth was still just scattered dust and rubble drifting through space. Then Jupiter did something stranger. It moved. It drifted inward toward the sun, then turned around and drifted back out. And in doing so, it rearranged the entire solar system before the rest of the planets had even taken shape. The asteroid belt, Mars, Earth's water, our position in space, all of it may trace back to this one early event. Tonight, we trace the fingerprints left behind in ancient meteorites and rewrite the story of how our solar system actually came to be. If stories like this, the quiet ones that rearrange how you see the solar system, it would mean a lot if you liked this video and considered subscribing, not for any big reason, just because it helps YouTube algorithm to keep showing you videos like this. Get comfortable, settle in 3, 2, 1, liftoff. $4,568,000,000 years ago, somewhere in a quiet, unremarkable region of a much larger galaxy, a cloud of gas and dust began to fall in on itself. There was nothing dramatic about it at first. No flash, no explosion, no announcement that anything was beginning. Just a slow, patient collapse, gravity pulling cold material inward, density rising, the cloud spinning faster as it shrank, the way a figure skater speeds up when she pulls her arms in close to her body. This collapsing cloud would eventually become our entire solar system, every planet, every moon, every asteroid, every comet, and every living thing that would ever exist within it, including you. But here is the part of the story that almost nobody tells correctly. When people imagine the first planet to form in this newborn system, they almost always picture something small, a rocky little world, maybe something like Mercury or Mars, a modest beginning before the bigger worlds came along. It feels intuitive. Small things first, big things later, build up from nothing. That is not what happened. The first planet to actually finish forming in our solar system was not small, it was not rocky, it was not anything like Earth. The first planet to complete its formation was Jupiter, an enormous ball of hydrogen and helium gas, and it did so while the inner planets, including the world you are standing on right now, were still little more than scattered dust and loose rubble drifting through space, bumping into each other, occasionally sticking together, mostly just floating in a kind of slow, directionless chaos. Jupiter was already a finished planet, fully formed, gravitationally dominant, while Earth had not even become a coherent object yet. This is not a story about which planet is the biggest. Jupiter being the largest planet in the solar system is common knowledge, the kind of fact that ends up on classroom posters and trivia questions. This is a story about something far less commonly understood, which is that Jupiter was first. And being first, as it turns out, changes everything that comes after, not because of size, but because of timing and sequence, and the order in which events are allowed to unfold. To understand why this matters, we have to go back to the very beginning, to that collapsing cloud of gas and dust, and we have to understand what it actually looked like in those earliest moments. Picture a vast, roughly spherical cloud, made mostly of hydrogen, with smaller amounts of helium and trace amounts of heavier elements, the leftover debris from earlier generations of stars that had lived and died long before our sun ever existed. This cloud was cold, dark, and enormous, spanning a region of space that would eventually be compressed down into something far smaller. As gravity pulled this material inward, the cloud could not simply collapse into a single point. Conservation of angular momentum, the same physical principle that makes a spinning top stay upright and a thrown ball curve when spun, meant that any small initial rotation in the cloud would become more pronounced as the cloud shrank. The cloud began to flatten, spreading out into a disk, with most of the material concentrating into a dense central region that would become the protosun, and the remaining material spreading out around it in a thin, rotating disk of gas and dust. This structure, the protoplanetary disk, is the stage on which everything else in this story takes place. It would have looked, from a great distance, something like a flattened pancake of material orbiting a young, still-forming star, with the star itself glowing faintly as gravitational compression heated its core, though nuclear fusion had not yet ignited. The disk was not uniform. It was hotter near the center, close to the protosun, and progressively colder as you moved outward. This temperature gradient turns out to be one of the most important features of the entire story, because it determined what kind of material could exist in solid form at different distances from the young sun, and that, in turn, determined how quickly planets could grow in different parts of the disk. The way astronomers actually arrive at a temperature structure for a disk that disappeared 4.5 billion years ago is itself worth pausing on, because it is not guesswork. Models of protoplanetary disks combine several streams of evidence. One stream comes from observing other young star systems that are still in the process of forming planets today, systems where telescopes can directly measure the temperature of the disk material at different distances from the central star by observing the wavelengths of light the disk emits, since warmer material radiates more strongly at shorter wavelengths and cooler material radiates more strongly at longer wavelengths. Another stream comes from the composition of meteorites themselves, which preserve direct chemical evidence of what temperatures the material they are made of experienced before it solidified, since different minerals only form or only remain stable within specific temperature ranges. By combining what is observed in other young systems with what is measured in the oldest surviving fragments of our own system, researchers can construct a reasonably consistent picture of how temperature varied with distance from the protosun in our own disk during its earliest stages, even though no instrument was there to record it directly at the time. Close to the protosun, temperatures were high enough that only materials with very high melting points, like rock and metal, could condense into solid grains. Water and other compounds like ammonia and methane would have existed only as vapor in this region, unable to freeze into ice because it was simply too warm. Further out, however, beyond a certain distance from the protosun, temperatures dropped low enough that water vapor could condense directly into ice. This boundary, the line beyond which water ice could exist as a solid in the protoplanetary disk, is what astronomers call the snow line, and its location is absolutely central to understanding why Jupiter formed first. The exact location of the snow line in our early solar system is something scientists have worked to estimate using models of the protoplanetary disk's temperature structure, and while the precise distance is still refined as research continues, most current estimates place the early snow line somewhere in the region beyond the present-day asteroid belt, in the general vicinity of where Jupiter orbits today, though the line itself would have moved inward over time as the disk cooled and the young sun's output changed. It is worth being clear about why the snowline moves at all, since this is sometimes a point of confusion. Early in a disk's life, the protosun is still contracting under its own gravity, and this contraction releases energy, making the young star and the inner disk around it considerably brighter and hotter than they will be once the star settles into a more stable, long-lived state. As the protosun's luminosity gradually decreases over the first few million years, the entire disk cools, and the snow line, the boundary at which the local temperature drops below the point where water ice can persist, creeps inward toward the sun over time. What matters for this story is the location of the snow line during the very earliest window, the first one to a few million years, when the most rapid phase of giant planet formation appears to have taken place. And during that window, the snow line sat far enough out that the region where Jupiter's core began assembling itself was on the cold side of it. What matters for this story is not the exact number of astronomical units, but the consequence of crossing that line. Inside the snow line, the only solid building material available for forming planets was rock and metal. Outside the snow line, in addition to rock and metal, there was also a substantial amount of water, ice, and likely ices of other compounds as well, all of which could condense into solid grains and contribute to planet formation. This might sound like a relatively minor difference, a bit more raw material in one part of the disk compared to another. It was not minor, it was transformative. Water, in the form of ice, is one of the most abundant condensable materials in a young star system, because hydrogen and oxygen, the two elements that combine to form water, are both extremely common, oxygen being one of the more abundant heavier elements produced by earlier generations of stars, and hydrogen being the most abundant element in the universe. When the temperature drops low enough for this water to freeze, it adds an enormous amount of additional solid mass to the available planet-building material in that region of the disk. Estimates suggest that beyond the snow line, the total mass of solid material available for building planets could have been several times greater than the mass of solid material available at a similar distance inside the snow line, where only rock and metal grains could form. This is the first piece of the puzzle. The region of the disk beyond the snow line, the region where Jupiter would eventually form, had access to dramatically more solid building material than the region closer to the protosun, where the rocky planets, including Earth, were forming. More available material meant that solid bodies in that outer region could grow larger and grow faster than their counterparts closer in. But having more raw material available is only part of the story. The other part is what happens once a growing body reaches a certain size, and this is where we need to talk about a process called core accretion, and a phenomenon that planetary scientists sometimes refer to, somewhat dramatically but not inaccurately, as runaway gas accretion. In the earliest stages of planet formation, throughout the entire protoplanetary disk, both inside and outside the snow line, the process worked roughly the same way. Tiny grains of dust, no larger than the particles of smoke or fog, collided with each other due to the natural motions within the disk. Sometimes these collisions caused the grains to bounce apart. But sometimes, due to weak electrostatic forces, or simply the right combination of speed and angle, the grains stuck together. Over time, through countless collisions, these grains built up into larger and larger clumps, first becoming pebble-sized, then boulder-sized, then eventually growing large enough that their own gravity began to play a meaningful role in attracting additional material. These larger bodies are called planetesimals, and they ranged in size from roughly that of a small asteroid up to bodies hundreds of miles across. There is a step in this process that researchers have spent a great deal of effort trying to understand, sometimes referred to as the meter-sized barrier, because it describes a genuine difficulty in the theory rather than a smooth, uncomplicated climb from dust grain to planetesimal. Objects somewhere in the range of a few feet to a few tens of feet across within a gas disk tend to experience a kind of aerodynamic drag from the surrounding gas that can cause them to drift inward toward the protosun relatively quickly, on time scales that, if nothing intervened, would be far shorter than the time needed for those objects to grow larger through collisions alone. In other words, if growth from dust grains to planetesimals proceeded purely through one-on-one collisions, getting gradually bigger, a huge fraction of the solid material in the disk would simply spiral into the protosun and be lost before it ever had the chance to become a planetesimal at all. The fact that planetesimals clearly did form, since we have their remnants today in the form of asteroids and meteorites, tells researchers that some additional process, beyond simple collisional growth, must have helped certain regions of the disk concentrate solid material efficiently enough to jump across this size range relatively quickly. For instance, through local concentrations of solid particles in turbulent eddies within the gas, which can become dense enough to collapse directly under their own gravity into a planetesimal-sized object, effectively skipping over the slow, drift-dominated middle ground. This is mentioned here not as a digression, but because it underscores something important for everything that follows, which is that the regions of the disk with more available solid material, such as the region beyond the snow line, would have had a head start in clearing this difficult size range as well, simply because there was more raw material available to concentrate in the first place. Once planetesimals reached a certain size, gravity became the dominant force driving further growth. Larger planetesimals had stronger gravitational pulls, which allowed them to attract nearby material more efficiently, which made them grow even larger, which strengthened their gravitational pull even further. This created a kind of positive feedback loop, sometimes called runaway accretion, in its own right, though this is a different process from the runaway gas accretion we will discuss shortly, in which the largest bodies in a given region of the disk grew disproportionately faster than their smaller neighbors, eventually pulling ahead to become what planetary scientists call planetary embryos or protoplanets, objects that were beginning to resemble true planets in terms of having significant mass and their own gravitational influence, but which had not yet finished growing. This process, from dust grains to planetesimals to planetary embryos, happened throughout the disk, both inside and outside the snow line, but the speed at which it happened depended heavily on how much solid material was available in any given region, because more material meant more collisions, more opportunities for growth, and a shorter path to reaching the size where gravity took over and accelerated the process further. This is where the snow line's advantage becomes decisive. In the region beyond the snow line, where water ice supplemented the available rock and metal, planetary embryos could grow to substantial sizes relatively quickly, reaching masses many times that of Earth, while the inner solar system's embryos were still comparatively small. And here is where the story takes its most important turn. Once a planetary embryo in the outer disk grew large enough, something remarkable happened. The embryo's gravity became strong enough not just to attract additional solid material, but to begin pulling in the surrounding gas of the protoplanetary disk itself. the hydrogen and helium that made up the vast majority of the disk's total mass. At first, this gas accretion was a relatively slow process. The growing embryo would pull in gas, gradually building up an atmosphere around its solid core. During this early phase, the mass of gas the embryo accumulates and the mass of its solid core grow at roughly comparable rates, with the gaseous envelope slowly thickening around the core, like a coat being layered on one thin sheet at a time. But there is a critical threshold, often referred to as the critical core mass, a mass at which the embryo's gravity becomes strong enough that it can pull in gas faster than the gas envelope can settle and cool to make room for more. Up until this threshold, the growing gaseous envelope is able to support itself against further collapse, with pressure from the gas balancing the inward pull of gravity. Once the combined mass of the solid core and its surrounding envelope crosses this critical threshold, however, the envelope can no longer hold itself up against its own weight. It begins to contract, and as it contracts, it heats up and radiates energy away, which lowers the pressure supporting the envelope even further, allowing it to contract more, which lets in more gas from the surrounding disk, which adds more mass, which increases the gravitational pull, which allows even faster accretion of additional gas. Once an embryo crosses this threshold, gas accretion enters this runaway phase. The embryo begins pulling in gas at an accelerating rate, its mass increasing rapidly, which increases its gravitational pull, which allows it to pull in gas even faster. This runaway gas accretion phase can add an enormous amount of mass to a planet in a relatively short period of time, astronomically speaking, transforming a solid core that might have been somewhere in the range of 10 times the mass of Earth into a gas giant hundreds of times more massive than Earth. This is, in essence, the story of how Jupiter formed. A solid core built from rock, metal, and water ice in the region beyond the snow line grew large enough, fast enough, to cross the threshold for runaway gas accretion, and then rapidly accumulated a massive envelope of hydrogen and helium gas, becoming the gas giant we observe today. And, critically, this entire process, from the initial growth of the solid core through the runaway accumulation of gas, appears to have happened on a timescale dramatically shorter than the timescale on which the rocky inner planets were forming. It is worth dwelling for a moment on just how different these two timescales actually are, because the difference is not a matter of being somewhat faster or somewhat slower. The protoplanetary disk itself, the gas component of it specifically, does not last forever. Observations of other young star systems show that the gas in a protoplanetary disk tends to disperse, either by being blown away by radiation and particle outflows from the central star, or by being gradually accreted onto the star itself or onto the planets that have already formed, on a timescale generally estimated to be somewhere in the range of a few million to around 10 million years after the disk first forms. This means that any process which depends on the presence of substantial amounts of gas in the disk, including runaway gas accretion, has a hard deadline. If a planetary core has not reached the critical threshold for runaway gas accretion before the surrounding gas disk disperses, it never will, and the resulting planet, no matter how large its solid core eventually becomes, will end up as a rocky or icy world without a massive hydrogen and helium envelope, rather than as a gas giant. Jupiter's core, based on the evidence we are about to walk through in detail, crossed this threshold and completed its runaway gas accretion phase within a window of just 1 to a few million years, comfortably inside the lifetime of the gas disk. The terrestrial planets, by contrast, including Earth, took tens of millions of years to fully assemble, a timescale that extends well beyond the point at which the gas disk had already dispersed entirely. While Jupiter's core was rapidly assembling itself in the outer disk, taking advantage of the extra solid material available beyond the snow line and then crossing the threshold into runaway gas accretion, the region of the disk where Earth would eventually form was undergoing a much slower, more gradual process. Without the additional boost from water ice and without crossing any threshold that would trigger a runaway growth phase, the embryos in the inner disk grew steadily but slowly through repeated collisions and mergers of smaller bodies, a process that would continue not for a few million years, but for tens of millions of years. While Jupiter was already a fully formed gas giant, its core complete and its massive gaseous envelope already accumulated, the future Earth was likely still in the form of multiple separate planetary embryos, perhaps a handful of Mars-sized or smaller bodies, still on a collision course with each other, still tens of millions of years away from the series of giant impacts that would eventually merge them into the single planet we live on today. This is the wrong kind of first. Not first in terms of size in any simple sense, though Jupiter is of course also the largest planet, but first in terms of completion, first in terms of having reached a finished state, while everything else in the system was still very much a work in progress. And this sequencing, Jupiter finishing while everything else was still unfinished, is not just an interesting historical footnote. It is the foundation for everything else that happened afterward, because a fully formed gas giant, sitting in the outer solar system while the rest of the disk was still full of gas, dust, and partially formed planets, is not a passive bystander. It is a massive gravitational presence, and massive gravitational presences do not sit still. They interact with their surroundings. They pull on things, and sometimes they move. But before we can talk about how Jupiter moved and what that movement did to the rest of the solar system, we need to address a more fundamental question. How do we actually know any of this? How can scientists working today, more than 4.5 billion years after the fact, determine not just that Jupiter formed before the inner planets, but roughly how quickly it did so and roughly when? In absolute terms, this all took place. The collapsing cloud of gas and dust that became our solar system is gone. The protoplanetary disk dispersed billions of years ago. There is no direct record, no photograph, no observational data from the time itself. The answer to how we know any of this is written, quite literally, into rocks, specifically into meteorites, the fragments of ancient planetesimals and protoplanetary material that have survived, in some cases essentially unchanged, since the very earliest days of the solar system, and which occasionally fall to Earth, where scientists can collect them and study them in laboratories using techniques of extraordinary precision. The story these meteorites tell, when read correctly, is the story of a chemical divide that opened up in the protoplanetary disk within the solar system's first few million years, a divide so significant and so persistent that its signature can still be detected in rocks today, and that divide points directly back to the early formation of a massive body in the outer solar system. That divide is the fingerprint Jupiter left behind, and reading that fingerprint is where we go next. Meteorites are, in a very real sense, time capsules. Most meteorites that fall to Earth originated as fragments of asteroids, themselves the remnants of planetesimals and protoplanets that never finished growing into full-sized planets, having either been gravitationally disrupted, collided with other bodies, or simply remained too small and too far from sufficient material to ever complete the planet formation process. Because these bodies formed early in the solar system's history and, in many cases, have remained largely unaltered since then, the material within them preserves a chemical record of conditions in the protoplanetary disk at the time and place where they formed. When scientists study meteorites, one of the most powerful tools available to them is the analysis of isotopes. To understand why isotopes matter so much here, it helps to remember what an isotope actually is. Every element is defined by the number of protons in its atomic nucleus, but atoms of the same element can have different numbers of neutrons, and these variants are called isotopes. Most isotopes are stable, meaning they do not change over time, but some isotopes are radioactive, meaning they decay over time into other isotopes, often of different elements entirely, at a rate that is precisely known and constant, described by what is called a half-life, the time it takes for half of a given quantity of the radioactive isotope to decay. This radioactive decay is incredibly useful for dating ancient materials, because if a rock contains a radioactive isotope and that isotope decays into a different isotope at a known rate, then by measuring the ratio of the original radioactive isotope to its decay product within the rock, scientists can calculate how much time has passed since the rock formed and the decay process began. This is the basic principle behind radiometric dating, and it is one of the foundational tools that allows scientists to determine the age of the solar system itself, an age of approximately 4,568,000,000 years, derived primarily from the radiometric dating of some of the oldest known meteorite materials. But the story of Jupiter's early formation involves something slightly different from simple radiometric dating of a single object's age. It involves comparing the isotopic compositions of different groups of meteorites to each other and discovering that these groups fall into two distinct chemical families that remained separate from each other for a specific window of time early in the solar system's history. Meteorites are broadly classified into several categories based on their composition and structure. But for this story, the most relevant distinction is between two broad groups, often referred to in terms of the isotopic reservoirs from which their parent body's material originated. One group, generally associated with what are called carbonaceous chondrites among other meteorite types, shows isotopic signatures consistent with material that formed in the outer regions of the protoplanetary disk, beyond the snow line. The other group, generally associated with ordinary chondrites and related meteorite types, shows isotopic signatures consistent with material that formed in the inner regions of the disk, closer to the protosun. Researchers studying this divide often use a pair of shorthand labels for these two groups, referring to the outer disk group as the carbonaceous, or CC, reservoir, and the inner disk group as the non-carbonaceous, or NC, reservoir, and these labels show up throughout the scientific literature on this topic precisely because the distinction between them turns out to be so fundamental. What makes this distinction so significant is not simply that these two groups have different isotopic signatures, which on its own might just reflect the natural variation you would expect across a large protoplanetary disk. What makes it significant is that these two isotopic reservoirs appear to have remained distinct, essentially uncontaminated by each other, for a specific and measurable window of time, generally estimated to be on the order of the first 1 to 4 million years of the solar system's history. Material from the outer reservoir and material from the inner reservoir did not significantly mix with each other during this early period, even though both regions were part of the same continuous protoplanetary disk, with no obvious physical wall or boundary separating them. This is, when you sit with it for a moment, a genuinely strange observation. If the inner and outer regions of the protoplanetary disk were part of a single continuous structure with gas and dust flowing through it, you might expect material to gradually mix and circulate between these regions over time, blurring any initial isotopic differences. But the meteorite record shows that this mixing did not happen, or at least did not happen significantly, for several million years. Something was preventing material from the outer disk and material from the inner disk from mixing freely. Something was acting as a barrier. The most widely accepted explanation for this barrier, and the explanation that connects directly back to the story of core accretion and runaway gas accretion we discussed in Part 1, is that the barrier was Jupiter itself, or more precisely, Jupiter's rapidly growing core and its gravitational influence on the surrounding disk. As Jupiter's core grew large enough to begin clearing a gap in the gas and dust of the disk around its orbit, a process that growing planets are understood to do through their gravitational interactions with the disk material, it would have created a kind of dynamical barrier, a region where the normal flow of material through the disk was disrupted. Material from beyond Jupiter's orbit would have had difficulty migrating inward past this barrier, and material from inside Jupiter's orbit would have had difficulty migrating outward past it, at least for as long as this gap persisted, and Jupiter's gravitational influence remained strong in this configuration. It is worth being concrete about what clearing a gap actually means in physical terms, because it is easy to picture this as Jupiter physically blocking a road, which is not quite the right image. A planet embedded in a disk of gas exerts a gravitational pull on the gas around it, and this pull is not uniform. It is strongest on the gas closest to the planet's orbit. As the planet's gravity tugs on this nearby gas, it transfers energy and angular momentum to that gas, pushing some of it slightly inward and some of it slightly outward, away from the planet's immediate orbital path. If the planet is massive enough, this effect becomes strong enough to push gas away from its orbit faster than the disk's own internal flows can refill that region, and the result is a partially evacuated lane, an annular gap, centered on the planet's orbit, with somewhat higher density gas on either side of it. This gap does not need to be completely empty of material to act as a barrier. It simply needs to reduce the rate at which material flows across it compared to the rate at which it would flow if the gap were not there, enough that, over a span of a few million years, the inner and outer reservoirs accumulate a measurable chemical difference, rather than blending into a single uniform composition. The timing here is the crucial piece. For this barrier to explain the isotopic dichotomy observed in meteorites, Jupiter's core would need to have grown large enough to create this gravitational barrier within the first 1 to 4 million years of the solar system's history, the same window during which the isotopic reservoirs remain separate. This is precisely the time frame that current research, including isotopic dating studies of iron meteorites, which represent the cause of differentiated planetesimals and therefore preserve some of the earliest formation signatures available in the meteorite record, points to for the formation of Jupiter's core. Iron meteorites deserve a bit more explanation here, because they play a particularly important role in this story, and the reason they do comes down to how they formed in the first place. Many of the planetesimals that grew large enough in the early solar system experienced a process called differentiation, in which the planetesimal's interior became hot enough, generally due to the decay of short-lived radioactive isotopes that were present in the early solar system in much greater abundance than they are today, for its material to partially melt. When this happens, denser materials, primarily molten iron and nickel, sink toward the center of the body under gravity, while lighter, rockier material rises toward the outside, in much the same way that oil and water separate into layers when left undisturbed. This process produces a planetesimal with a metallic core surrounded by a rocky outer layer, a structure in miniature very similar to the layered structure of Earth itself. Iron meteorites are fragments of these metallic cores, exposed and broken apart after their parent planetesimals were later shattered by collisions with other bodies, sending pieces, including these core fragments, scattering through the solar system, some of which eventually found their way to Earth. Because the differentiation process that formed these cores happened very early, while the short-lived radioactive isotopes that drove the internal heating were still present in meaningful quantities, iron meteorites preserve a record from extremely close to the very beginning of the solar system's history, making them especially valuable for the kind of early timeline questions this story is built around. Walk through how scientists actually measure isotopes of elements like molybdenum and tungsten in these iron meteorites, and the process is one of remarkable precision applied to extremely small samples. A small piece of an iron meteorite, often just a fraction of an ounce, is carefully cleaned to remove any surface contamination it may have picked up since landing on Earth, since even brief exposure to Earth's atmosphere, soil, or moisture can introduce terrestrial material that would muddy the isotopic signal researchers are trying to read. The clean sample is then dissolved using a combination of strong acids, breaking it down into a solution containing all of its constituent elements mixed together. From this solution, researchers chemically isolate specific elements of interest, in this case molybdenum and tungsten, using a technique that exploits subtle differences in how different elements interact with specially prepared resins, allowing the molybdenum and tungsten to be separated out from everything else in the sample, including from each other, in a sequence of careful chemical steps. Once isolated, the molybdenum and tungsten are analyzed using an instrument called a mass spectrometer, a device that can sort atoms by their mass with extraordinary precision, distinguishing between isotopes that differ from each other by the mass of a single neutron, and counting, in effect, how many atoms of each isotope are present in the sample. The output of this process is a set of ratios. For instance, the ratio of one molybdenum isotope to another, or one tungsten isotope to another, expressed as tiny deviations from a reference standard, deviations that are often only a few parts in 10,000, but which are measured with enough precision and reproducibility that they can be reliably compared between different meteorite samples. By measuring the relative amounts of two specific molybdenum isotopes designated by their atomic masses as molybdenum-94 and molybdenum-95, alongside two specific tungsten isotopes, tungsten-182 and tungsten-183. Researchers analyzing a set of iron meteorites drawn from several different iron meteorite groups, representing the cores of multiple distinct ancient planetesimals rather than just one, identified two distinct populations. One population showed isotopic ratios consistent with formation closer to the Sun than Jupiter's current orbit, and the other showed ratios consistent with formation farther from the Sun. Crucially, the tungsten isotope measurements also allowed the researchers to estimate when each of these planetesimals differentiated. Since tungsten 182 is itself the decay product of a short-lived radioactive isotope of hafnium that was present in the early solar system, meaning the tungsten ratios serve a dual purpose, both identifying which reservoir a meteorite's parent body belonged to, and providing a clock for when that parent body's core formed. The results showed that both populations, the inner and outer reservoirs, existed and were actively forming differentiated planetesimals at the same time within a window beginning around 1 million years after the start of the solar system and extending to somewhere between 3 and 4 million years afterward, all while remaining isotopically distinct from each other. This distinguishes them clearly from the rocky planet's own formation timeline. The terrestrial planets, including Earth, did not finish forming within this 1 to 4 million year window. Their formation, as discussed in Part 1, stretched over tens of millions of years, involving the gradual buildup of planetary embryos, followed by a later phase of giant impacts between those embryos. The iron meteorites that reveal the inner and outer reservoir dichotomy are not samples of the terrestrial planets themselves. They are samples of smaller planetesimals, bodies that differentiated and formed their metallic cores quickly within those first few million years, but which never grew large enough to become full planets, remaining instead as the parent bodies of the asteroids we see scattered through the solar system today. The terrestrial planets were assembled later, out of a population of these and similar bodies, over a much longer span of time. It is worth pausing here to be clear about what is confirmed observation, what is strong interpretation, and what remains more open to refinement, because this is exactly the kind of distinction that matters in good science communication. The isotopic dichotomy itself, the existence of two distinct isotopic reservoirs in meteorites that remained separate for a window of several million years, is a confirmed observation measured directly through isotopic analysis of meteorite samples using techniques like mass spectrometry, which can detect incredibly small differences in the ratios of different isotopes within a sample. The interpretation that this dichotomy was caused by a gravitational barrier created by Jupiter's growing core is a strong interpretation, supported by the timing match between the isotopic dichotomy and independent estimates of when Jupiter's core would need to have formed based on models of core accretion and runaway gas accretion, but it remains an interpretation rather than a direct observation, since no one was there with a measuring instrument 4.5 billion years ago to confirm the mechanism directly. A useful way to think about the difference between these two levels of confidence is that the isotopic dichotomy is something you could, in principle, hand to any laboratory with the right equipment and have them measure for themselves, and they would get the same numbers. The attribution of that dichotomy to Jupiter's core, by contrast, is the best current explanation for those numbers, the one that fits most naturally with everything else we understand about how planets form and how disks behave. But it is an explanation rather than a measurement, and like any explanation in science, it remains open to being refined, or in principle replaced, if some other mechanism were ever found to explain the same observation equally well or better. What this isotopic evidence gives us, taken together with the theoretical understanding of core accretion and runaway gas accretion from Part 1, is a remarkably consistent picture. A planetary core began forming in the outer protoplanetary disk, beyond the snow line, taking advantage of the additional solid material available there in the form of water ice, in addition to rock and metal. This core grew rapidly, reaching a size sufficient to begin clearing a gap in the surrounding disk material within the first few million years of the solar system's history. A gap that acted as a barrier preventing the free mixing of material between the inner and outer disk. A barrier whose effects are still detectable today in the isotopic compositions of meteorites that fell to Earth in recent centuries. Based on the size a core would need to reach in order to produce a gap capable of maintaining this kind of isotopic separation, researchers have estimated that Jupiter's core had likely grown to somewhere in the neighborhood of 20 times the mass of Earth within that first million years alone, a core mass well above the critical threshold needed to trigger runaway gas accretion. And once this core reached a sufficient size, it crossed that threshold, rapidly pulling in hydrogen and helium gas from the surrounding disk, and becoming, in a relatively short span of time, the massive gas giant we now call Jupiter. Meanwhile, in the inner disk, the embryos that would eventually become the rocky planets were still growing slowly through the gradual accumulation of solid material, a process that would continue for tens of millions of years, rather than the few million years that appear to have been sufficient for Jupiter's core to form and then rapidly accrete its gaseous envelope. By the time Earth's formation process was complete, involving, as it likely did, a series of collisions between multiple planetary embryos, culminating in at least one giant impact event, Jupiter had already been a fully formed planet for tens of millions of years, sitting in the outer solar system, massive, gravitationally dominant, and very much finished with the process of forming. This brings us to the question that sits at the heart of everything that follows. A fully formed gas giant planet, sitting in a protoplanetary disk that is still full of gas, dust, and partially formed planetary bodies, does not simply remain a passive, isolated object. It exists within a dynamic environment, surrounded by gas that is itself orbiting the young sun, gas that the planet's own gravity continues to interact with even after the main phase of accretion has ended. And these interactions between a planet and the gas disk around it can have a profound effect on the planet's orbit itself, an effect known as migration, in which a planet's distance from its star gradually changes over time. Not because the planet is being pushed by some external force in any simple sense, but because of the way its gravity interacts with the surrounding disk material, exchanging angular momentum with that material in ways that can cause the planet's orbit to slowly shrink, or in some cases, to expand. Jupiter, having formed first, having reached its final mass, while the rest of the solar system was still very much under construction, did not simply stay where it formed. The evidence suggests that Jupiter moved, migrating inward through the disk, potentially traveling a significant distance from its formation location toward the inner solar system, before something happened that reversed this migration and sent it moving back outward again toward roughly the orbit it occupies today. This migration and its reversal did not happen in isolation. It happened while the inner solar system was still in the process of building its planets, while the region that would become the asteroid belt still contained a substantial population of planetesimals and planetary embryos, and while the raw material that would eventually become Mars was still being assembled. A planet, the mass of Jupiter, moving inward through a disk that is also home to the building blocks of the rocky planets, and then moving back outward again, does not pass through unnoticed. Its gravity reaches out across enormous distances, stirring up the orbits of everything in its path, scattering material, exciting orbital eccentricities, and in some cases, ejecting bodies from the inner solar system entirely, or sending them on trajectories that would carry them to entirely different parts of the disk than where they originally formed. The asteroid belt that exists today, a sparse scattering of rocky bodies orbiting between Mars and Jupiter, containing only a tiny fraction of the mass that models suggest should have been available to form a planet in that region, may be a direct consequence of Jupiter's passage through this part of the disk. Mars, smaller than models of planet formation would predict for a planet at its distance from the Sun, if that region had been allowed to accrete material undisturbed, may similarly be a victim of sorts of Jupiter's migration, its growth cut short by the depletion and scattering of the material it would otherwise have continued to accumulate. This is the hypothesis known as the Grand Tack, named for the sailing maneuver in which a ship changes direction by turning its bow through the wind, a name chosen because it captures the idea of Jupiter's orbit making a kind of turn, moving inward and then reversing to move back outward, like a ship tacking against the wind before settling onto a new course. And it is to this migration, this tack, and its consequences for the asteroid belt, for Mars, and for the question of where Earth's water actually came from, that we turn next. Jupiter's gravity, having finished its main growth phase, while the rest of the disk was still thick with gas, did not leave it stationary. It began to migrate, and to understand what that migration actually means, mechanically, it helps to set aside any image of a planet being pushed or shoved by some outside hand. A planet embedded in a gas disk is constantly exchanging angular momentum with the gas around it through gravitational interactions. The planet's gravity raises spiral density waves in the disk, and the gravitational pull of those waves back on the planet can either remove angular momentum from the planet's orbit, causing it to spiral slowly inward toward the Sun, or add angular momentum to it, causing it to spiral slowly outward. Which of these happens, and how quickly, depends on the structure of the disk on either side of the planet, the distribution of gas, the local temperature, and the presence of other massive bodies nearby. For a planet the mass of Jupiter, embedded in a disk still rich with gas in the first few million years after the solar system's birth, the torques from the inner disk appear to have outweighed the torques from the outer disk, and the result was a slow, steady inward drift, Jupiter's orbital distance from the protosun shrinking over time, not in a single dramatic plunge, but as a gradual contraction playing out over hundreds of thousands of years. The proposal that this inward drift carried Jupiter a substantial distance, potentially down into the region where Mars orbits today, before something reversed the direction entirely and sent Jupiter migrating back outward toward roughly its current orbit, is what planetary scientists call the Grand Tack hypothesis. The name itself is borrowed from sailing, from the maneuver in which a ship moving against the wind turns its bow through the wind's direction in order to change course, and the name fits because what the hypothesis describes is exactly that, a single, continuous migration that includes a turn, an inward leg followed by a reversal, and an outward leg, rather than two separate, unrelated events. The most cited version of this hypothesis proposes specific numbers for this journey. Jupiter is thought to have formed at a distance from the Sun of roughly 3.5 astronomical units, an astronomical unit being the average distance between Earth and the Sun, used here as a convenient unit for measuring distances within the solar system. From that formation point, Jupiter's inward migration is proposed to have carried it down to a distance of roughly 1.5 astronomical units, a distance close to where Mars orbits today, before the reversal began, with Jupiter then migrating back outward to settle near its current distance of roughly 5 2/10 astronomical units. It is worth being precise about where this hypothesis sits in the landscape of current science. The idea that Jupiter migrated inward during the first few million years of the solar system's history, while the disk still contained enough gas to drive that kind of orbital change, is grounded in the same physics that astronomers now routinely apply to explain the orbits of giant planets discovered around other stars, many of which orbit far closer to their host stars than any planet in our own solar system, planets that almost certainly could not have formed in place at such close distances, and must have migrated inward from farther out. The general principle that gas giants migrate is, in that sense, well established. What remains more actively debated, and what the research requirement for this title specifically flags, is the precise distance Jupiter traveled, the precise timing of the reversal, and how cleanly the asteroid belt's current structure can be mapped back onto a single migration event versus a more complicated combination of factors. Some more recent modeling work has revisited the original grand tax scenario and suggested that Jupiter's inward excursion may not have needed to be quite as extreme as the earliest versions of the hypothesis proposed in order to produce the asteroid belt and Mars that we observe today, while still preserving the core idea that an inward then outward migration of the giant planets occurred and left a lasting imprint on the inner disk. So the broad shape of the story, inward migration, followed by a reversal driven by the giant planets, sits closer to a candidate explanation than a fully settled fact, even while the underlying physics of why giant planets migrate at all is on much firmer ground. The reversal itself is thought to be connected to the formation of Saturn. As Saturn's core grew and it too crossed the threshold into runaway gas accretion, becoming a second massive gas giant in the outer disk, the two planets would eventually have found themselves migrating in ways that brought their orbital periods into a particular numerical relationship with each other, a configuration known as an orbital resonance, in which the time it takes one planet to complete an orbit becomes a simple ratio of the time it takes the other planet to complete its orbit. For instance, one planet completing 2 orbits in the time it takes the other to complete 3. When two massive planets enter this kind of resonance, while still embedded in a gas disk, the combined gravitational effect of the resonance can change the direction of the torques acting on both planets, converting what had been an inward migration into an outward one. Under this picture, Jupiter's inward drift continued until Saturn caught up to it in this resonant sense, at which point the pair began migrating outward together, Saturn trailing behind Jupiter, both planets moving back toward the outer disk and ultimately settling into something close to the orbital configuration we observe today, with Jupiter at roughly 5 astronomical units from the Sun and Saturn farther out beyond it. This part of the story, the specific role of Saturn and the particular resonance involved, sits more toward the speculative end of the spectrum in terms of exact details, though the broad notion that the second giant planet to form played some role in halting and reversing Jupiter's inward migration is a recurring feature across multiple versions of this kind of model. What matters most for the rest of this story is not the precise distance Jupiter traveled or the exact resonance involved, but what a giant planet moving through the inner disk in either direction does to everything else that is trying to form there at the same time. And to understand that, we need to think about the region of the disk that, in our solar system today, sits between the orbits of Mars and Jupiter, a region occupied by the asteroid belt. The asteroid belt today is sparse. The combined mass of every object in the asteroid belt, every asteroid, every dwarf planet-like series which accounts for roughly a third of the belt's total mass on its own, every smaller fragment adds up to only a small fraction of the mass of Earth's moon, itself a body far smaller than Earth. This is strange when you consider that the asteroid belt sits in a region of the solar system that, based on models of how solid material was distributed in the early disk, should have contained enough mass to form a planet roughly the size of Mars or larger, not a scattered debris field containing barely more than a rounding error's worth of planetary material. Something removed the overwhelming majority of the solid material that originally occupied this region, and the Grand Tack offers a specific mechanical answer for what that something was. As Jupiter migrated inward during its initial leg of the tack, its gravity would have swept through the region that is now the asteroid belt, and a massive planet passing through a region populated by smaller planetesimals does not simply absorb everything in its path in any literal sense, a claim this episode is specifically avoiding making in that oversimplified form, because the planetesimals in this region were small and numerous, and Jupiter's gravity, rather than capturing all of them through direct collision or accretion, primarily worked by gravitationally exciting their orbits, increasing their eccentricities and inclinations. The measures of how elongated and how tilted an orbit is relative to the plane of the rest of the disk. A planetesimal whose orbit becomes highly eccentric or highly inclined due to repeated gravitational encounters with a passing giant planet is far more likely to end up on a trajectory that either sends it crashing into the Sun, ejects it from the solar system entirely on a hyperbolic trajectory that carries it out into interstellar space, or sends it on a collision course with one of the inner planets or with the giant planet itself. Across the population of planetesimals in this region, the net effect of Jupiter's passage, first inward and then, on the return leg, outward again, would have been a dramatic depletion, the vast majority of the original solid material, either ejected from the region entirely, consumed in collisions, or scattered onto orbits that carried it elsewhere in the solar system, leaving behind only a small, dynamically excited remnant population, which is what we observe today as the asteroid belt, a population whose orbits are, notably, on average more eccentric and more inclined than you would expect if this region had simply formed quietly and undisturbed. There is a further wrinkle to how this depletion is thought to have played out, one that addresses a question that might otherwise seem like an obvious problem for the whole idea. If Jupiter passed through the asteroid belt region twice, once moving inward and once moving back outward, you might reasonably expect the region to end up completely empty, swept clean on the first pass, and then swept clean again on the return trip, leaving nothing behind at all. But the asteroid belt is not empty. It is merely sparse, and the explanation for why anything survived at all is almost as important as the explanation for why so much was lost. According to the more detailed versions of this model, the region was indeed substantially emptied during Jupiter's inward passage. But as Jupiter and Saturn made their return journey outward, a small fraction of the planetesimals that had been scattered by the giants during their travels, planetesimals originally from a range of different starting locations across the inner and outer disk, were recaptured into stable orbits within the asteroid belt region as the giant planets passed back through and then moved on, leaving this repopulated, much smaller remnant behind them as they continued outward toward their final positions. This recapture process has a further consequence that connects directly to one of the asteroid belt's more puzzling features, which is that the belt today contains a genuine mixture of compositionally different objects, some that are rocky and relatively dry, more common toward the inner edge of the belt, and others that are more primitive, carbon-rich, and associated with a greater abundance of hydrated minerals, more common toward the outer edge of the belt. Under the grand tack picture, this compositional mixing is itself a direct, leftover signature of the migration. The drier, rockier objects repopulating the inner asteroid belt are thought to represent planetesimals that originally formed closer to the Sun than Jupiter's formation location, inside the snowline, while the more primitive, carbon-rich objects repopulating the outer asteroid belt are thought to represent planetesimals that originally formed farther out, beyond or between the orbits of the giant planets themselves, in the region where, as discussed in Part 2, water, ice, and other volatile compounds were abundant. Two populations of objects that, under undisturbed circumstances, would likely have remained separated by enormous distances, one population native to the inner disk and another native to the far outer disk, ended up scattered together into the same relatively narrow region of space, the asteroid belt, as a direct consequence of being caught up in the same giant planet migration, stirred together during the passages, and then left behind, side by side, when the giants moved on. This is the sense in which a planet's migration can be reconstructed mathematically from the present-day structure of the asteroid belt, not by directly observing the migration, which happened over 4 billion years ago and left no direct record, but by treating the asteroid belt as the residue of that migration, a population whose statistical properties, the distribution of orbital eccentricities and inclinations among the surviving asteroids, the locations of certain structural gaps within the belt corresponding to particular orbital resonances with Jupiter's current position, and the spatial mixing of compositionally distinct object types, encode information about the gravitational history that shaped it. By running simulations of Jupiter's migration under different assumed parameters, how far inward, how fast, when the reversal happened, and comparing the resulting simulated asteroid populations to the actual observed population, researchers can work backward from the present-day asteroid belt toward constraints on what the early migration must have looked like in order to produce what we see now. The same migration that depleted the asteroid belt's mass also appears to be connected to the small size of Mars, and the mechanism here, while related, is distinct enough to be worth separating out clearly. Mars today has a mass less than 1/10 that of Earth, despite orbiting in a region of the disk where models of planet formation that do not account for any external disruption tend to predict a planet considerably more massive, potentially comparable to Earth or Venus in size, should have been able to form from the material available at that distance from the Sun. The shortfall in Mars's mass, under the grand tack picture, is attributed to the same process that depleted the asteroid belt, the inward and outward passages of Jupiter and Saturn alongside it, stirred up and scattered a substantial fraction of the solid material in the broader region, spanning what is now the outer edge of the terrestrial planet zone and the inner edge of the asteroid belt, material that, in an undisturbed disk, would have continued to be available for the growing Mars embryo to accrete over the tens of millions of years that terrestrial planet formation requires. With that material gravitationally excited and scattered away, ejected from the region or sent onto orbits that no longer intersected Mars's growing orbit, the Mars embryo was effectively cut off from much of its potential feeding zone earlier than it otherwise would have been, and its growth stalled at a mass considerably smaller than it might have reached in an unperturbed disk. Earth and Venus, forming closer to the Sun, in a region less directly affected by Jupiter's passage, were able to continue accreting from a less disrupted local supply of material and reached masses much closer to what undisturbed models predict for their respective distances. There is a way of framing this that some researchers have used, which is worth introducing here, because it reframes the entire inner disk's history in terms of a boundary rather than a series of separate events. Under one influential formulation of this idea, the inward leg of Jupiter's migration effectively truncated the disk of solid material available for terrestrial planet formation at a sharp outer edge, at a distance from the Sun corresponding roughly to Earth's own orbit. In other words, rather than thinking of Jupiter as having selectively removed material from one particular region while leaving everything else untouched, this framing proposes that Jupiter's passage established an outer boundary for the terrestrial planet-forming disk itself, with essentially no significant reservoir of planet-building material left beyond that boundary afterward. Everything that formed inside that boundary, Mercury, Venus, Earth, and a stunted Mars built from whatever scraps of material happened to lie close enough to the boundary to still be accreted, formed from a disk that had effectively been given a new outer wall partway through its own construction. This framing has the advantage of explaining, in a single stroke, both why Mars is undersized and why there is essentially no additional planet, no fifth terrestrial world, sitting in the region between Mars and the asteroid belt, where models of an undisturbed disk might otherwise have predicted one could form. It is worth being clear that the existence of one influential modeling approach producing this kind of truncated disk picture does not mean every detail of it is settled science, but it does illustrate how a single migration event, properly modeled, can account for several otherwise separate puzzles about the inner solar system's architecture at once. It is worth being careful here about what this does and does not imply, because there is a version of this story that overcorrects into treating Jupiter's migration as a kind of wrecking ball that indiscriminately ruined the inner solar system, and that is not quite the right framing either. The depletion of the asteroid belt and the stunting of Mars represent a redistribution and a loss of material from a specific region, the outer reaches of the terrestrial planet zone and the region that became the asteroid belt, not a wholesale disruption of the entire inner disk. Earth's own formation process, the slow accumulation of planetary embryos over tens of millions of years, culminating in giant impacts, appears to have proceeded in a region of the disk that, whatever its details, ultimately produced a planet of roughly the mass we observe, suggesting that whatever disruption Jupiter's migration caused did not prevent the inner disk closer to the Sun from continuing to function as a planet-forming environment in a broadly normal way. The picture that emerges is one of a gradient of effects, strongest in the region Jupiter and Saturn passed closest to and lingered in longest, the asteroid belt region, and the outer edge of the terrestrial zone where Mars was forming, and progressively weaker, closer to the Sun, where Earth and Venus were assembling. But there is a further wrinkle here, and it is one that takes the story in a direction the simple framing of disruption and depletion does not fully capture on its own. The same gravitational scattering that removed material from the region near Mars's orbit and from the asteroid belt did not simply destroy that material or send all of it out of the solar system entirely. Some fraction of the planetesimals, that were gravitationally excited during Jupiter's passages would have been scattered onto orbits that carried them inward into the part of the disk where Earth itself was still in the process of forming. And the planetesimals that originally occupied the outer asteroid belt region, the region beyond roughly where the asteroid belt's outer edge sits today, are thought, based on the same isotopic reservoir distinction discussed in Part 2 in connection with the meteorite evidence for Jupiter's formation, to have been compositionally different from the material closer to the Sun, specifically richer in water, ice, and other volatile compounds, the same kinds of compounds that, beyond the snow line, supplemented the available solid material and gave Jupiter's core its early advantage in the first place. If a significant population of these water-rich, outer disk planetesimals was scattered inward by Jupiter's migration, and some fraction of those bodies ultimately collided with the still-forming Earth, depositing their water and other volatile content onto a young planet that, forming as it did closer to the Sun, in a region too warm for water ice to have condensed directly during the planet's main accretion phase, might otherwise have ended up considerably drier than the Earth we actually have. Then, the same migration event that depleted the asteroid belt and stunted Mars might also be implicated in the origin of a substantial fraction of the water that now fills Earth's oceans, sits in its mantle, and makes up the bodies of every living thing on its surface, including the audience listening to this sentence right now. This is, without question, one of the more compelling threads to pull on in this entire story. The idea that the very same gravitational event that scattered and depleted a region of the inner solar system might also be the reason Earth has the water it has. But it is also, and this needs to be stated with real precision rather than glossed over, one of the more actively contested and actively researched threads in the entire picture, and untangling exactly how much of Earth's water arrived this way, versus through other proposed pathways, versus having been present in the materials Earth accreted from in the first place, is not something that can be settled with a single clean answer, and is where we turn next. The question of where Earth's water actually came from is one that planetary scientists have been chipping away at for decades, and the honest answer, even now, is that no single source has been confirmed as the dominant one, which makes this a perfect place to slow down and look at how scientists actually test a hypothesis like this rather than simply asserting it. The primary tool here is, once again, isotopes, but a different isotope than the ones used to date Jupiter's formation. Where the molybdenum and tungsten isotopes discussed earlier in this story are useful for timing when a body's metallic core separated from its rocky outer layers, the isotope that matters most for tracing the origin of water is an isotope of hydrogen itself, ordinary hydrogen, the kind that makes up the overwhelming majority of hydrogen atoms anywhere in the universe, has a nucleus consisting of a single proton and nothing else. But there is also a heavier, stable isotope of hydrogen called deuterium, whose nucleus contains one proton and one neutron, making it roughly twice as massive as ordinary hydrogen, while still behaving chemically almost identically. When water forms, some small fraction of the hydrogen atoms within it will naturally be deuterium rather than ordinary hydrogen, and the ratio of deuterium to ordinary hydrogen within a given sample of water, a ratio astronomers and planetary scientists refer to using a shorthand based on the chemical symbol for deuterium paired with the chemical symbol for ordinary hydrogen, turns out to vary depending on where and how that water formed. This variation happens because deuterium and ordinary hydrogen, despite their chemical similarity, are not identical in terms of how they behave physically, particularly when it comes to processes like evaporation and condensation, where the slightly heavier deuterium tends to be left behind in liquid or solid water at a marginally higher rate than ordinary hydrogen during evaporation, a phenomenon related to what chemists call isotope fractionation. Over the long history of the protoplanetary disk, water that formed and existed under different temperature conditions at different distances from the proto-sun, and that was processed through different cycles of evaporation and condensation, ended up with measurably different deuterium to hydrogen ratios, depending on its formation, history, and location. And as a general rule, water that condensed farther from the proto-sun tends to carry a higher deuterium to hydrogen ratio than water that condensed closer in, giving this ratio a kind of directional quality, a fingerprint that hints at distance from the sun as well as composition. This gives scientists a tool. If Earth's water has a deuterium to hydrogen ratio that closely matches the ratio found in a particular class of meteorite, that match becomes evidence, though not proof on its own, that the meteorite class in question, or bodies compositionally similar to it, could plausibly have been a significant source of Earth's water. The deuterium to hydrogen ratio of Earth's oceans, measured using what is called standard mean ocean water as the reference point, comes out to approximately 1/5600 times 10 to the negative fourth power, a number that on its own means little until it is placed alongside the equivalent ratios measured in other solar system bodies. And this is where the carbonaceous chondrites, the same broad meteorite group that, in Part 2, was associated with the outer solar system isotopic reservoir, the reservoir whose separation from the inner solar system reservoir provided one of the key pieces of evidence for Jupiter's early formation, come back into the story, because carbonaceous chondrites are, on average, considerably richer in water, bound up within hydrated minerals in their rocky matrix, than the ordinary chondrites associated with the inner solar system reservoir, in some cases containing water making up close to 1/5 of their total mass. When researchers compare the deuterium to hydrogen ratio of water in Earth's oceans to the deuterium to hydrogen ratios measured in various carbonaceous chondrite samples, the match, for at least some carbonaceous chondrite subclasses, is closer than the match between Earth's water and water associated with comets, the icy bodies originating from much farther out in the solar system, in the region beyond Neptune's orbit, whose deuterium to hydrogen ratios have been measured directly by spacecraft that have flown past or landed on cometary nuclei, and which, for several comets studied this way, come out several times higher than Earth's ocean ratio. This comparison has, over the past few decades, shifted the balance of opinion among many researchers away from comets as the dominant source of Earth's water and toward asteroid-like bodies, specifically those compositionally similar to carbonaceous chondrites, as a more plausible major contributor. One particularly striking piece of supporting evidence came from a meteorite that fell over the United Kingdom and was recovered within roughly half a day of landing, fast enough that researchers were able to analyze its water content before it had meaningful time to absorb moisture from Earth's own atmosphere, a contamination problem that affects most older meteorite finds. And the deuterium to hydrogen ratio, measured in this freshly recovered sample, matched Earth's ocean water remarkably closely. But more plausible major contributor is a long way from confirmed sole source, and there are real complications that keep this question genuinely open rather than settled. For one, The deuterium to hydrogen ratio match between Earth's oceans and carbonaceous chondrites, while closer than the match with comets, is not a perfect match across the board, and different carbonaceous chondrite subclasses themselves show some spread in their ratios, with detailed measurements on individual mineral grains within these meteorites, revealing that what looks like a single bulk ratio at first glance can actually be a mixture of a deuterium-poor water component and a more deuterium-rich organic component, blended together in proportions that differ from one meteorite group to the next, meaning that even within the broad category of carbonaceous chondrite-like bodies, identifying a single specific population as the source requires more precision than a simple bulk comparison can provide. For another, and this is a complication that has become considerably more prominent in research over the past several years, Earth's mantle, the thick layer of rock beneath the crust that makes up the bulk of the planet's volume, itself contains water, locked within mineral structures rather than existing as liquid, and measurements of this mantle water have, in some cases, returned deuterium to hydrogen ratios noticeably lower than the ratio measured in ocean water, closer, in fact, to the ratios measured in a different meteorite group entirely, the astatite chondrites, a group of meteorites whose overall isotopic composition closely resembles that of Earth's rocky material in general, and which were traditionally assumed to have formed too close to the Sun and to be too dry to have contributed meaningfully to Earth's water budget at all. More recent work analyzing hydrogen content directly within samples of N-statite chondrites found considerably more hydrogen locked within them than had previously been assumed, with a deuterium to hydrogen ratio close to that of Earth's mantle, raising the possibility that a substantial portion of Earth's total water, particularly the water now residing deep within the planet rather than in the oceans, may have been present in the very materials Earth was built from in the first place, accreted locally from the inner disk rather than delivered later by impacts from farther out at all. What this leaves us with is a picture in which Earth's total water budget may not have a single uniform origin at all, but may instead represent a mixture, water, that was present in the materials Earth originally accreted from in the inner disk, evidenced by the mantle's isotopic signature, supplemented by some additional contribution from impacting bodies that arrived later, evidenced by the closer match between ocean water and carbonaceous chondrites, with the relative proportions of these different contributions still being actively debated and refined as more precise isotopic measurements become possible, including measurements from sample return missions that have brought back material directly from carbonaceous asteroids in recent years, material that can be analyzed in laboratories on Earth with a level of precision that meteorite falls, having been exposed to Earth's atmosphere and surface environment after landing, cannot always match. So where does the Grand Tack fit into this picture? Specifically, the proposed connection is this. If carbonaceous, chondrite-like bodies are indeed a significant contributor to at least part of Earth's water, particularly the ocean-like signature, those bodies needed some mechanism to get from wherever they originally formed, generally thought to be farther from the Sun than the region where Earth itself was assembling, to orbits where they could actually collide with the growing Earth. Jupiter's migration, both the inward leg and the outward leg, by gravitationally scattering planetesimals from the region around and beyond what is now the asteroid belt, provides exactly this kind of mechanism, a way of taking material that originally formed in a water ice-rich part of the disk and redistributing some fraction of it onto orbits that crossed into the inner solar system, where it could be accreted by Earth, Venus, and Mars, over the tens of millions of years, those planets were still forming. Some modeling work, focused specifically on this question, has examined whether the rapid gas accretion phases of Jupiter and Saturn, the same runaway growth episodes discussed in Part 1, could on their own have scattered enough icy, carbon-rich planetesimals inward to account for a meaningful fraction of the inner solar system's water budget, independent of exactly how far Jupiter's orbit itself migrated, treating the scattering of material as a consequence of the giant planets simply existing and growing rapidly in that region of the disk, rather than requiring the full, inward, then outward orbital excursion of the Grand Tack specifically. This does not mean the Grand Tack is required for Earth to have gotten water from carbonaceous, chondrite-like sources. Other mechanisms for scattering material inward from the outer asteroid belt region have also been proposed, including gravitational interactions that did not necessarily require a large-scale migration of Jupiter's orbit at all. Simply the ongoing gravitational influence of a Jupiter that had already reached roughly its current mass and orbit, perturbing the orbits of nearby planetesimals over long timescales without itself needing to move very far. What the Grand Tack offers is one specific, well-modeled pathway by which this delivery could have happened, a pathway that emerges naturally from the same migration event already invoked to explain the asteroid belt's depletion and Mars's small size, which gives it a certain explanatory economy, several otherwise separate puzzles potentially resolved by a single underlying cause. But that explanatory economy is not the same thing as proof, and the honest state of the field is that the relative contributions of different water delivery pathways and the precise role of any single migration event versus longer-term, lower-intensity scattering remain active research questions rather than closed cases. There is one more piece of context worth placing here, briefly, because it is the kind of thing that often gets folded into stories about the early solar system's violent history in a way that can create a misleading impression of a single, simple narrative. The late heavy bombardment refers to a period evidenced primarily by the ages of impact craters and impact melted rocks collected from the Moon, during which the inner solar system, including the Earth-Moon system, appears to have experienced an elevated rate of impacts from leftover debris at some point after the main phase of planet formation had largely concluded. For a time, this bombardment was widely linked, in a fairly direct causal sense, to a separate dynamical event involving the giant planets, a later instability sometimes referred to as the Nice model, named after the city in France where the researchers who proposed it were working, in which the orbits of Jupiter, Saturn, and the ice giants Uranus and Neptune underwent a period of gravitational instability and rearrangement, distinct from and occurring well after the early Grand Tack migration discussed throughout this episode, an instability that, in some versions of the model, was proposed to have flung a wave of icy and rocky debris from the outer solar system inward, contributing to the cratering recorded on the Moon. It is important to be clear that the Nice model and the Grand Tack are not the same event and should not be conflated. The Grand Tack, as described throughout this episode, is proposed to have occurred within the first few million years of the solar system's history, while the disk still contained substantial gas, and while the terrestrial planets were still in their main accretion phase. The Nice model's proposed instability, by contrast, is generally placed at a later point, after the gas disk had already dispersed entirely, involving gravitational interactions among the fully formed giant planets and a remnant disk of icy planetesimals beyond Neptune, rather than interactions within a gas-rich disk. and the once tight link between this later instability and the lunar late heavy bombardment has itself become less certain in recent years, as more detailed analyses of lunar samples and crater ages have raised questions about whether the bombardment represents a single, sharply defined spike in impact rates at all, or whether it may instead reflect a more gradual decline in impact rates from an already elevated post-formation baseline, a decline that could produce a similar pattern in the crater record without requiring a discrete, later triggering event. None of this changes the core story this episode is built around: the early formation and migration of Jupiter and its consequences for the asteroid belt, Mars, and the inner disk's water budget. But it is worth flagging precisely so that the grand tack is not mistaken for, or blurred together with, this separate and later chapter in the solar system's dynamical history, which remains its own area of ongoing research. What all of this leaves us with, when we step back from the individual threads, the snow line, the isotopic dichotomy, the migration, the asteroid belt's depletion, Mars's stunted growth, the water question, is a picture of the early solar system in which a single sequence of events, beginning with the simple fact that more solid material was available beyond the snow line than inside it, and ending with a fully formed giant planet, moving inward and then outward through a disk that was still actively building the rest of the planets, set in motion a chain of consequences that did not finish playing out for tens of millions of years, consequences that are still, in a very direct sense, written into the structure of the solar system we observe today, in the asteroid belt's sparse and dynamically excited population, in the disproportionately small mass of Mars relative to where it sits, and quite possibly, though this remains the most actively debated piece, in at least some portion of the water that makes up the oceans of the planet beneath your feet and beneath the device you are using to listen to this right now. This is the point in the story where it becomes worth asking what kind of fact this actually is. The fact that Jupiter finished forming first. It is tempting, when laying out a chain of cause and effect like this. Snow line leads to early core leads to runaway gas accretion. Runaway gas accretion leads to a fully formed giant planet. That planet migrates. The migration depletes the asteroid belt and stunts Mars, and possibly delivers some of Earth's water, to start treating the whole sequence as a kind of inevitability, as though once the snow line existed in the place it did, everything else followed in a more or less predetermined way, including, eventually, a planet with oceans and an atmosphere, and, much later, a species capable of building telescopes and writing scripts about the deuterium to hydrogen ratio of its own seawater. That is not quite the right way to hold this story, and it is worth being precise about why. The order in which things form in a protoplanetary disk is not a minor detail that gets sorted out after the real planet formation has happened. It is closer to being the schema for the resulting structure, the underlying template that determines what kinds of planets end up where, how much material is available to each of them, and what their compositions look like before any of the planets have even finished growing. In our solar system, that schema happened to produce a particular outcome: a giant planet finishing first in the outer disk, migrating through the inner disk while it was still under construction, depleting one region, redistributing material into another, and leaving behind a terrestrial planet zone with one undersized world, one severely depleted debris field, and at least one planet, the third one out from the Sun, that ended up with the right combination of size, position, and water content to develop the conditions we associate with habitability. But nothing about the underlying physics of core accretion, snow lines, and giant planet migration guarantees that particular outcome. Change the timing slightly. Change the amount of material available in the outer disk. Change how far Jupiter's inward migration carried it before the reversal. Change whether a second giant planet formed quickly enough and in the right configuration to trigger that reversal at all, and the resulting solar system could look quite different, perhaps with a more massive Mars and a less depleted asteroid belt, but a drier set of inner planets, or perhaps with a giant planet that migrated all the way into the region where Earth itself was forming, scattering the material that would have become Earth entirely before it had a chance to assemble. This is not a statement of cosmic pessimism, and it is not meant to suggest that Earth's habitability was some kind of lucky accident in a sense that diminishes it. It is simply an honest acknowledgement that the particular sequence of events that produced our solar system's architecture was one possible outcome among a range of outcomes that the same underlying physics could, in principle, produce under slightly different initial conditions, and that recognizing this is exactly what allows scientists to do something genuinely useful with this knowledge, which is to start asking the same questions about other planetary systems. Over the past 3 decades, the discovery of thousands of planets orbiting other stars has given astronomers a dataset that did not exist when ideas like the Grand Tack were first being developed. A dataset that includes systems with giant planets in all kinds of configurations, some orbiting extremely close to their host stars in a way that strongly implies inward migration on a scale that would, if it happened in our own solar system, have carried a giant planet through the entire terrestrial planet zone and out the other side, others with giant planets in wide orbits, and a great many systems that, when surveyed carefully, appear to lack large gas giants entirely, at least within the range of orbital distances current detection methods are sensitive to. When researchers attempt to model the formation and evolution of rocky planets in these other systems, the presence, absence, mass, and orbital history of any large gas giants in that system, particularly the question of whether such a planet formed early and whether its formation and any subsequent migration would have carried it through the region where smaller, potentially rocky planets might otherwise form, has become one of the variables increasingly treated as important, alongside more commonly discussed factors like a star's size, temperature, and the distance at which liquid water could exist on a planet's surface, when assessing what kind of terrestrial planets and what kind of water budgets a given system might plausibly produce. This does not mean that a system needs a Jupiter analog in order to host a habitable planet, and it would be a mistake to read this episode as making that claim. There is ongoing scientific discussion about systems that appear to lack large gas giants altogether, and about what such systems might mean for the formation and water content of any rocky planets they do contain. Discussion that has not converged on a single answer about whether the absence of a giant planet is, on balance, more favorable or less favorable for the development of an Earth-like world, given that a giant planet's early formation and migration can be either a source of disruption, scattering material away from where smaller planets are trying to form, or a source of delivery, redistributing water-rich material into the inner disk. Depending on the specific details of timing and distance, the same dual nature that this episode has tried to keep in view throughout, rather than collapsing into a simple story of protection or destruction. What the existence of our own solar system read through the lens of Jupiter's early formation and migration, does offer is a worked example, a single case where the formation order of the planets and the migration history of the first one to finish can be traced through specific, measurable evidence, isotopic ratios in meteorites, the orbital structure of the asteroid belt, the deuterium content of seawater, and connected to the present-day architecture of an entire planetary system, including the one habitable world within it. There is something worth sitting within the fact that the evidence for all of this exists, in the end, in rocks. The isotopic dichotomy that places Jupiter's core formation within the solar system's first few million years is read out of meteorites, fragments of bodies that formed in that same disk, that survived for over 4 billion years, often as parts of larger asteroids, before being knocked loose by some collision and eventually falling to Earth's surface, where someone picked them up, or where a dedicated search team found them lying on the ice in Antarctica or in a desert, and where a laboratory, using instruments capable of distinguishing between isotopes that differ from each other by a single neutron's worth of mass, measured ratios precise enough to place that meteorite's parent material into one of two reservoirs that stopped mixing with each other within a window of a few million years, out of a solar system that is now 4,568,000,000 years old. The asteroid belt's depleted mass and excited orbits are read out of telescope surveys that have catalogued hundreds of thousands of individual asteroids, plotting their orbital eccentricities and inclinations, and comparing the resulting statistical distribution to what simulations predict under different migration scenarios. And the question of Earth's water is read out of the ratio of two isotopes of hydrogen, present in vanishingly small relative abundance, in samples of ocean water and in samples of meteorites, and increasingly in samples brought back directly from asteroids by spacecraft. None of this required anyone to have been present 4.5 billion years ago. It required the right rocks to survive, the right instruments to be built, and the right questions to be asked of the data those instruments could produce. And what those rocks, those orbits, and those isotope ratios collectively describe is a solar system whose final architecture, the number and size of its rocky planets, the existence and structure of its asteroid belt, and the water content of at least one of those planets was substantially determined within the first few million years of its existence, by which body finished forming first, and by where that body went afterward. Earth, as it exists today, with its particular mass, its particular orbital distance from the Sun, and its oceans, is not separate from this story. It is one of the outcomes of it. The same sequence that left Mars undersized and the asteroid belt sparse also, by whatever combination of pathways turns out to have been most significant, left Earth with at least some portion of the water it has, and Earth's main accretion process, the slow assembly of planetary embryos over tens of millions of years, played out in a part of the disk that, whatever disruption Jupiter's passage caused elsewhere, remained capable of producing a planet of roughly the size and composition we observe. None of this was decided by Earth. It was decided, in large part, before Earth existed as a single body at all, by a sequence of events involving a different planet entirely, one that had already finished, gas envelope and all, while Earth was still several collisions away from becoming a world. That is the shape of the story this episode has tried to tell. Not a story about Jupiter as a guardian standing watch over the inner planets, and not a story about Jupiter as a destroyer that wrecked everything in its path, but a story about timing, about a sequence of formation events that played out over the solar system's first few tens of millions of years, in an order that placed a fully formed gas giant in motion through a disk that was still building everything else, and about how that order, more than almost any single event within it, shaped the solar system we have, including the part of it we happen to live on. Sleep gently now, traveler, for the worlds above were shaped before you ever drew your first breath.